Hey students, I thought I'd make a quick video here, kind of maybe helping you with the equations and keeping your thoughts together because as you've heard me many times say that one of the challenging parts of thermodynamics is the fact that a lot of our equations are what we call path dependent. In other words, what equation you must use for either the thermal energy or the work energy kind of depend on what process you're doing with your gases. Like, are you warming them at constant temperature or constant pressure? Are you expanding them at constant temperature, or are you doing it adiabatically? And so that's this whole idea here. So I thought maybe kind of a summary chart could be helpful. Let me draw a line here. I'll do a double line. But we might have, and I'll call it the easiest case, volume is held constant. And so we called that the isovolumetric case. And maybe to give myself a little bit of room, I'll put a space between here. But another common one we do is warming it or cooling it at constant pressure. And so that's the isobaric case. The other one is when we leave the temperature a constant, and that's the isothermal case. And the other one is where we do a process where we don't let heat energy, enter or leave, and that means the energy can only enter or leave the system by work. And so this one, I'll say again, always confuses students at the beginning because they think, well, if no heat energy can go in and out, there's no change in temperature, so how is this different than this one? And the truth is that the energy can still go in and out. It just has to be restricted to going in and out by work, and therefore the temperature can go up and down, which is kind of the unique one here. The temperature remains constant, and yet you have energy either enter or leave the system by work. Then there has to be a Q, and so this one, the Q does not equal to 0. And of course, then this one, the change in temperature does not equal to 0. And that is a little bit hard to digest for the beginning student. Anyway, that's not quite what I wanted to focus on here. I wanted to then say that for a lot of our problems, and particularly now that we got into chapter 22 and we're actually applying these ideas, we are going to, have to calculate things like the thermal energy and then the work, and then the change of the internal energy. And I thought maybe making a little video here. Oh, you know what? And maybe, how about, let's just talk PV equals nRT for a second. But before I get there, let me just go back here to the energies, because, again, what's kind of interesting is you want to pay attention to what process is going on. And so a lot of times we have like a PV diagram that has a cycle, and one process is constant volume, and another process is constant pressure, and another process is constant temperature, and another process is adiabatic. So when you do all that, I would suggest you kind of keep all these formulas in mind. And I like to start off by saying, okay, which one of these are zeros? And of course, 0 for Q in the adiabatic process. Since work has to do with a force times a distance, the equation for work in the isovolumetric would be 0. And since the internal energy is related to the kinetic energy, and kinetic energy is related to temperature, constant temperature would be a constant, no change in internal energy. And so these are the equations you would use for each of these cases. Now, another nice one to do after the zeros is the change in internal energy. Because if you think right here about the thermal energy, this is why we invented the phrase molar specific heat at constant volume, because then we just take the number of moles, multiply by this number, times the delta T, and then we get the thermal energy. It's also why this one is kind of nice, NCP delta T. This was our argument that, you would have a different and bigger number. So in other words, Cp would be greater than Cv during the constant pressure one. But my point is that if you're calculating heat, you can see here that I've got 3 different equations for 3 different times. We got 4, but this is the hardest one, so I'll do that one last. But this is my chance to emphasize that I've got different equations for different scenarios. If I ask how much heat, I have to say, well, what process is it? Because if it's adiabatic, it's 0. If it's isovolumetric, it's this one. And if it's constant pressure or isobaric, it's this one. And if it's isothermic, it's going to be this one before we're done here. Okay. And so that's what I mean by saying we have a different equation for different scenarios, because these are each path dependent. But watch this. This is kind of nice. Remember, these two, the first law of thermodynamics, say these two have to add up to that one. So this would be Cv delta T, since this one is 0. And here's what is really, really nice is this one is not path dependent. And so if you derive the formula, which we just did under the case of constant volume, it's not restricted to just constant volume because it is a state function. It has nothing to do with the path you take. So even if you warm it up by some delta T under constant pressure, you could still calculate it using this same formula that we derive for constant volume. And that's always a weird one to think that, okay, I'm going to use this formula, which has the molar specific heat at constant volume, but I'm using it during the constant pressure process. And that's just kind of weird. And I get that, but that's why I'm making this little video to emphasize when to use which equation. And you could even then see it. Technically, I've actually used this equation right here, because if we're doing the constant temperature and I'm using this same equation, delta T is 0. So I'll just put a 0. So I would argue that this really is the same equation. And then down here, it is the same equation. And so it's kind of nice, and that's why I say do this one second in terms of calculations, your delta E, because the zeros are very easy. So do your zeros first, but then second to that, do this column, do your delta E's, because it's the same equation regardless of what process. It only depends on the change in temperature. That's it. And of course, like I said, it may bother you at first that you're using a variable that says specific heat at constant volume, molar specific heat at constant volume, even though you're doing like the adiabatic or the isothermic or the isobaric, but it does work. And so the ones that are harder are really these two columns, the heat energy and the work energy. This one's pretty straightforward. It's a state function, and that's why I said once we derived it once, we're golden. All right, maybe at this point, I would then say, since these two have to add up to that one, maybe the best thing to do is to use this equation for the work done during the adiabatic. Now, technically, you might say this. You might say, well, isn't work then negative the integral of P dV? Yes. Well, and then in the adiabatic process, isn't pressure times volume to a power of gamma equal to some constant? So couldn't we replace pressure with whatever this constant is, which would depend on the problem, how much gas we have. But then also, then it would be volume to gamma, and then we can integrate. And yes, we could do all that. And I'll just stop right there. That's what I'm trying to avoid. We don't need to do that. That would be the harder way to get the same answer. I'll just say if we did a lot of work by doing this integral for work, we would get that equation when we're all said and done. Actually, in the meantime, we might have some equation for the volumes. In fact, that's a homework question for you. But let me not put it in our summary because this is far easier to get. So I'm going to say, although this is not wrong, it is not usually the best way to go. And so this would be my recommendation to use this equation when you're calculating the work for adiabatic. And again, it still might bother you because you have this, the molar specific heat at constant volume, and you're doing an adiabatic process, and you're talking about the work being done, which depends on the path, and both of those reasons are just screaming at you saying, don't use CV, but it does work because of that logic I just went through, that these two have to add up to that one, and this one has to be the same as that one, and so it does work. And so that, to me, is one of the weirdest ones, because, like I said, again, here I'm using an equation of constant volume, and I'm not using a constant volume process. And I'm even doing a calculation that I know is path dependent, but yet it works. So that's kind of the big one here. Now, again, trying to summarize these formulas, you could then do the same logic for the work done at constant pressure. You would just say, well, why don't you just move this, to the other side, and then you would have this minus that. And so you would have something like N, and then you would have like a CV minus a CP times a delta T. And although that's true, and I kind of put it up here, this one could also be very easily done with this integral, because this integral is really easy with constant pressure. Now, a moment ago when I did adiabatic, it wasn't so easy, and I stopped short of completing it. But this one is real nice because at constant pressure, I can just pull the P out in front, and then I just get an integral from initial volume to final volume, which I can just write as minus P delta V. And so that one's probably worth putting in here as P delta V, that I could do either one of those. And so had I already done these two, in other words, if I knew the delta T's right away, I'd probably do that one and then get my work by this one. But if I knew how the volumes changed, I'd probably do this one first, because neither one of those are real hard. All right, so let's see. So we got all the equations we would use at constant volume, and all the equations we would use at constant pressure, and all the equations we would use adiabatic. Here is the last one. And fortunately, as you can see, if these two are going to add up and give me that, at least these are equal and opposite. So let me just figure out the easier one of the two. And it turns out the work we already did back in chapter 20. Let's do that again here. I'll do this integral yet again, minus the integral of P dV. And in this case, we know, and I guess I started to write it here, PV equals to nRT. In fact, I'm kind of doing the same thing I did with the adiabatic. I'm just going to put in what pressure is equal to. And so this one is a little easier. Actually, I would even say a lot easier than this one. Maybe not quite as easy as this one, but this one's not bad. And we're have to do it. So whether it's good or not, like adiabatic, I didn't actually have to do it. So I took the easy way out. But here, I've just, no matter how hard it is, I've got to do it. Unfortunately, it's not too hard because when you recognize that it's a constant temperature process, the isotherm, you can pull all the constants, including temperature, out in front, and you just get an integral of dV over V. So you get minus nRT, the natural log of final volume over initial. And so going into this little box here for the work at constant temperature, I'll put nRT natural log of final volume over initial. And I guess I kind of went outside of my box there. Okay. And that's the one that I did last purposely because I think it's the hardest. But then if I jump over to here, the heat energy then is just equal and opposite. So there it is. These are the four equations, and this is what I was saying here at the beginning. The equation you would use for heat would be different in all four cases. And that's why we have to know what path we're doing. And likewise for work. The equation we would use is different in all four cases. So we got to pay attention to which process we're doing. And this is our state function. The equation we would use for all four cases is the same. Just like I kept using the analogy of 1/2 mv squared. You know, we can talk about a roller coaster that is speeding up because of some reason, or it's sped up too fast and slowed down. We can still always use 1/2 mv squared for the kinetic energy of the roller coaster. Kinetic energy is a state function in mathematics. It only cares about the initial and final velocity, not how it got there. So we always use this equation for kinetic energy, just like we always use this equation for the change in internal energy. But these are equations depend on how you get there, sort of like friction does. And so friction would depend on, you know, how it got there. And so a roller coaster that goes down and up and then down again to get to that final speed traveled a much longer path than one that just went straight, you know, down towards the final speed, and therefore the amount of friction is path dependent. And so these are the kind of things we did in mechanics, that how you got there determined how much work was done by friction. The change in kinetic energy was path independent. And that's what we're doing here in our thermodynamics. But I think it is a little harder than mechanics. Now, that was my original plan, to just do those. And so I'll say that I'm just going to add to this. And so if you're still watching, it's kind of nice to remember then that PV equals nRT is true for a gas anytime, anywhere, all the time. So it kind of fits this same phrase that I could use this equation here for any of these processes. But in each of them, something is restricted, and so we can modify this for that particular case. For example, constant volume. So if you had like initial pressure and a volume and initial temperature, there's no point in calling it initial volume. A moment later, after you warm it up, let's say, you would now have some final temperature and then some final pressure. And so if you subtract the initial and final, or final from initial, you would get the change in pressure times the volume is equal to nR times the change in temperature. And so this equation right here, the changing in pressure and the changing in temperature, go together in the special case of constant volume. And following that same logic, in the case of constant pressure, I would have an initial and final volume and just a pressure to deal with. I would then have a pressure times change in volume equals nR delta T. And so I would use this only in the case of constant pressure, and I would use this only in the case of constant volume. And then, of course, likewise, if I had constant temperature, I would have PV equals to, I'll just call it a constant, nRT. Of course, that constant would depend on its temperature and the number of moles, so I can't tell you what the constant is. But what I can say is now pressure and volume have an inverse relationship, meaning if the pressure went up, the volume would go down. Or the other way around, if the volume went up, the pressure would go down. I guess we refer to that as Boyle's law. And so that's the connection between the pressure and volume of a gas at constant temperature. So nice to use it. And again, only would use that at constant temperature. And so again, taking the more general equation, PV equals nRT, and applying it to constant volume, constant pressure, constant temperature, so isovolumetric, isobaric, and isothermic. The harder one, and we all did this in chapter 20, but we waited until chapter 21 to get to the adiabatic, and we showed that pressure times volume raised to a power of gamma is equal to a constant. Now again, that constant would be equal to the number of moles and the temperature. In fact, usually the best way to get that constant is to say, okay, well, I have some initial pressure and I have some initial volume, and so if I raise it to a power of gamma, that's going to be my initial constant. Sometimes you might even just avoid the constant pressure and its number and then just set it equal to final pressure, final volume raised to gamma. And maybe not even calculate this constant, but just do that mathematics, and then one of these you know and one you don't, so you solve for. And so good. I hope that summarizes everything for you. Maybe one more comment should be made, or maybe two. First one being about gamma. Gamma is the CP over CV. And in order to get gamma, you get it from CP and CV. But the way you get CP is you get that from CV. You take CV and you add an R to it. And the way you get CV is you do the number of degrees of freedom and you multiply by 1/2 R. And so if I was trying to figure out, say, gamma for a diatomic molecule like nitrogen, let's say, I would think about a nitrogen molecule and say it can move left and right. There's 1 degree of freedom. Up and down, there's another degree of freedom. Forward and back, there's another degree of freedom. It can rotate around 2 axes. The third one is kind of a picture of a cylinder, a very narrow cylinder, so it doesn't count for much. So there would be 5 degrees of freedom. And so the CV for nitrogen would be 5/2 R. And then the CP would then become 7/2 R. So this would be the CV for nitrogen, CP for nitrogen. And then the gamma is that ratio, which is 7/5, which is equivalent to 1.4 in a decimal form. So the idea of getting either gamma or CP or CV all comes down to one piece of information: how many degrees of freedom. So you got to look at what kind of gas you have, and that kind of gives everything away. And so keep that in mind. That's how you get the gamma. The other thing I should say before I kind of leave here is we had another value of Q, calculating thermal energy, that we were first introduced to in chapter 19. It's a little too elementary that we don't use it too much, but it is the specific heat, where it is really the mass specific heat. For example, we learned that aluminum had a specific heat of 0.22 calories per gram per each degree Celsius you warmed it up. And notice that that is very different than the molar specific heat. So when we're dealing with a gas, we don't like to use the specific heat that's based upon mass. It's not very useful. That's because the specific heat depends on whether we have constant volume or constant pressure. And so the reality is we do these type of calculations for gases because then they expand and do work. And we do these kind of calculations for solids and liquids because a solid and a liquid can't really expand. And so you don't have any of this. And so it doesn't really make much sense to label things in the number of moles. It's just nice to measure the specific heat in the number of grams you have. It's kind of more practical. You have a block of aluminum and you're going to go put it on a scale and get its mass to see how much aluminum you have. And so it's easier to specify how much aluminum you have by mass than it is by the number of moles. But for a gas, we can't do that. The gases behave based on how many you have, not how much they weigh. And so if I have a container of a bunch of oxygen and the same number of nitrogen, even though they don't have the same mass, they have the same number of moles. And so it's better to talk about the connection to the number of particles you have when you do with a gas as opposed to the mass for a liquid or a solid. So use this when you're doing any kind of heat energy related to solids and liquids. Use these when you're talking, and actually 1, 2, 3, 4, either of these 4 equations when you're talking about the heat for a gas: constant volume, constant pressure, constant temperature, and adiabatic. All right. Well, I hope I wasn't too long-winded. I wanted to keep it under 20 minutes, and I missed that by 5 minutes. But hopefully that kind of summarizes a lot of what we did in our thermodynamics and what equations we have. All right. Take care.